Next speaker is Dr. Gu Yuanjie. Dr. Gu Yuanjie is an assistant professor lecturer at Imperial College in London, England. He's a maintainer of the RT Thread community and one of the 3 international code reviewers for RT Thread. He's also one of the 2 joint leaders of the open source power system analyzing toolbox, Simplest Grid Tool. And he's the founder of the hardware in the loop simulation system, Simplest Real Time, which may go some way to explain why the title of this presentation is OpenPowerware, porting RT Thread for power electronics. So, Dr. Gu Yuanjie, over to you.
Thank you, Max. Just to confirm, can you all hear me?
Yeah, we can hear you and we can see your slides.
That's great. I'm gonna open my camera, and that's not me. That's my demo, which I'm gonna show a little bit later.
We wondered about that earlier on. It was like, what's that? Where did that come from?
Oh, so that's motor drive systems, and that's related to my topic today.
Awesome. Right, we're looking forward to see that. Okay.
So, and thank you for your introduction, Max. Basically, I'm just actually a power electronic engineer, and I mainly work for the power industry. And so, power is one of the main consumers for embedded systems. We have many embedded CPUs in wind turbines, in motor drive, in electric vehicles, but for most of the power electronic applications, the embedded software development is on bare metal, which is awful. But people have to live with that. And the reason is actually threefold. So the first reason is that the power electronic control requires a very high performance real time. So it requires very low latency. So the latency must be below, say, a microsecond, which is beyond the capacity of any real-time operating system. And the second reason is the cost sensitivity. So the electronic industry, so they operate in terms of economy of scale. So say an inverter is sold 1 million times each year. And so if we can push down a single penny of cost on any of these products, it's a fortune. So people just use cheaper MCUs to push down the cost. And because of the lack of capacity on these MCUs, so you can only use bare metal to realize the functions. And the third reason is actually culture. So most of the power engineers, they are trained as hardware developers, so they are not so used to the patterns or the paradigms of software development. And these are the 3 reasons why bare metal is the mainstream solutions for the power electronic industry. But the tides are really changing at the moment, and say people like me are quite fed up with bare metal development, and we are looking for different alternative solutions. And the reason is also threefold why people are moving on. So the first reason is the increasing software complexity. So we have, say, reconfigurable control for inverters, for motor drives, and we also have network control. It's not just a standalone inverter. So these inverters are organized in the network, and they communicate to each other with some central control unit. And so the control is becoming more complicated. And sometimes we also want to deploy edge computing on these control MCUs. So the software becomes more and more complicated. And the second reason is the embedded engineers in the power industry is getting more expensive. And so in order to run bare metal codes on these devices, we have to keep an expensive team of embedded engineers who just maintains these codes, and people have to calculate which one is cheaper, either to use, say, easier software development tools, which need a little bit more investment in the hardware, but in return you get to reduce the number of embedded engineers, and that's another reason. And the third reason is the increasing capacity of MCUs. I mean, the Moore's law is continuing, so the capacity of the MCU is increasing, and the cost of a single capacity is reducing. So the things that used to be considered expensive are no longer expensive. So people can tolerate using a better MCU without using too much cost. And because of these reasons, so people are thinking, can we just use a better software development tool chain instead of bare metal for electronic control? And of course, one of the things to think about is to use RTOS. And the benefit is quite apparent. So we can accelerate the software development for rapid development, and also for tuning. Tuning takes a lot of time, and also for repurpose the software. And the codes are more portable than the bare metal codes. They are reusable, so it makes hardware migration and upgrade much easier than using bare metal, and also offers more features of security. And say, like, the RTOS offers mechanisms of synchronization like semantics and semaphores, which are not existed in bare metal development. And so in the bare metal development, so the developer have to think of his own synchronization mechanisms, which sometimes can have bugs inside. And these bugs are very hard to debug. So the benefit is quite straightforward. But there's also some challenges. Yeah, the one I mentioned, so the zero latency. So the power electronic control requires a very small latency. And also there's some special devices, say the PWM and the encoder for motors, and the special-made, tailor-made ADC devices. These are, say, quite different to the mainstream peripherals on MCUs. And also there's some special architecture like this one. So the TI-C28 DSP MCU. So it's a mainstream device for the power industry, but it's quite different to the standard architecture like ARM and RISC-V. And so the target of this presentation is to introduce our recent effort to address these challenges under the initiative of OpenPowerware. So the name is actually inspired by OpenFirmware, and we transformed to power. So it's an open source software for the power electronic industry. And the target is to port the RTOS to make them more suitable for the power industry. And we have selected RT-Thread to be the first try to achieve this target because of the very fantastic ecosystem and the community of RT-Thread. So we want to make this development the first try to be based on the RT-Thread. And in this presentation, I'm going to introduce our recent effort in porting RT-Thread to make it suitable for electronic control. Yeah, so the first task is to address the challenge of zero latency response. So we know that the RTOS introduced latencies, and the most so the well-known one is the contact switch for threads. It takes some time to save the context and do the shredding algorithm and switch to another context. It takes time. And so people ask, we do not use threads, we just use interrupt. Of course, you can do that, but even for interrupt, you still have latency introduced by RTOS. And the reason is that, so during context switch, you have to disable the global interrupt because the interrupt can compromise, can corrupt the context switching process. So we have to disable the interrupt during the context switch and enable that after that. And if there's an interrupt that occurs, is triggered at this time, it means they can only be responded, it can only be served after the context switch is over. And this induces extra latency for the interrupt response. And so we have done some testing, say on our MCU, so the context switch. So the time duration for the context switch to disable the interrupt is going to be around 1 microsecond. And so we have a MCU that has 200 megahertz. And if the frequency is lower, so the latency is going to be higher. And say a couple of microseconds on the scale. And this latency is in most of the applications is not a problem, it's just a technical. But for power industry, for power electronic control, it makes differences. So people can't tolerate that. So we have to eliminate this latency on the microsecond time scale. And how do we do that? So, so we introduced a concept of super real-time interrupt. And this super real-time interrupt just run in parallel with the RTOS. So, so the idea is during the context switch, so the mainstream solution is to disable the global interrupt, and we do not do that. So we only disable part of the interrupt and leave some other interrupts, what we call the super real-time interrupts, enabled. And then even during the context switch, we can still serve these super real-time interrupts. And we have to keep in mind that during the super real-time interrupts, we can't invoke any RTOS services, so as not to corrupt the context switching process. So we keep the context switching enacted, and we just do the ISR interrupt service routine without touching the RTOS. And then after the routine is finished, you give the control back to the RTOS. So they are like two parallel universes. They do not talk, and they do not affect each other. They do not hamper each other, but they do talk to each other via, say, this wormhole. So this is synchronized, right? So if there's any need, needs of data communication between the super real-time interrupts and the RTOS, we can use some synchronization mechanisms. But we can't use anything related to the RTOS itself. We can't use mutex, we can't use semaphore, but we can use memory-based synchronization, say ping-pong mechanism or ring buffer, which is not related to the RTOS. So we can use these techniques to do the synchronization between the two parallel universes. So this is the way we deal with the first challenge, to ensure zero latency interrupts for the RTOS. And the second challenge is on the specialized devices. So one of the features of RTT, it has a very good device model. And so to make device management really easy. But for power electronics, so the peripherals, the devices for the power electronic-based MCUs, they are quite specialized. And in this slide here, I just show the PWM's peripheral, and we see that is actually a quite complicated system. And And if you click into each of these subsystems, is also another, say, a block diagram. So it's kind of a lot of registers to be configured, different modes, which is quite different to the standard to the standard peripherals, like the ones in ARM, Cortex, and 4. And this peripheral is designed to realize some specialized control functions for electronics. For example, in this picture here, we show what we call the peak current mode control. So the idea is to turn on the transistor until the current reaches some peak value, and then turn it off until and after turning off, the current will reduce until you turn it on again. So, and this means that the PWM has to be well coordinated with ADC, so that you know what is time to turn off when the current has reached the maximum value. And this is very different to conventional PWM and ADC devices. And the PWM and ADC, they are also interlocked. So the PWM may trigger the ADC, and ADC may, set different duty cycles for the PWM, and this is very different to the conventional PWM and ADC. And there's 3 different options. So, I mean, for these kind of devices, how do you define device models to be a good abstraction of the device? So people do not have to consider too much about the hardware details, and can use some high-level, say, APIs to do the control of these devices. We need some sort of abstraction or model, and the question is how we do that. And there's 3 options. The first is based on the RT-flat device framework, which is great. And it also opens some flexibilities. Say the device model opens some OPS callbacks, and you can just define your own APIs based on that callback, which is good. But this may limit the flexibility of the PWM. Say we want the PWM to be interlinked to ADC. This is not existing in the current RTT device model. So if we want to use the RTT intrinsic native model, it has to limit some flexibilities in the devices. And the second option is to circumvent the RTT device framework and design a dedicated device framework for power electronics. And this may leave up some RTOS services, but this will better flexibility and also have smaller overhead compared to the RTT's native device framework. And there's another option is just to simply use the hardware abstraction layer of the vendor. Say the STM or the NFC devices, they provide a very good help which you can use. But the problem is that health for different vendors is very different. And even say for the TISC28 MCUs, there is no health, and all the health is very bad. And that means if you use the health, you limit the portability of the code. So we think that the option 2 is the preferred direction to go, and it takes some time to realize that, because you have to design a new framework, and which is not so easy actually. So we implemented option 1 and option 3 in our existing code, and the aiming was implementing option 2 maybe next year. So this is the second challenge, and the third one is about the special CPU architecture. For example, this one, the C28, which I mentioned, is a very weird device. So the first problem is about the alignment of the address. So for 16-bit variables, there's no alignment. There's only alignment for 32-bit, and this causes huge troubles for us for porting. And the second is the interrupt enable register. So this register is pushed to the stack in the interrupt service routine. And that means this register is part of the context. And that means if you enable one interrupt in one thread and you switch to another thread, then this interrupt becomes disabled because it carries with the thread. It does not carry with the thread. And this is not what we want. So if say we want to, if we enable the one interrupt in the main thread, we want the other thread to be able to respond to that interrupt as well. And this is also problematic. And the third issue is that the exception. So we need some kind of exceptions to trigger the OS exceptions to trigger the context switch, handle the context switch. And the TI's C228 device, they do have such an exception, but this exception is not maskable. That means whenever you trigger this, it's going to be responded, even in the interrupt. And that means, and this also created a lot of troubles for us in the porting and importing the context switching assembly code. And but fortunately, we managed to solve all these problems. For the first one, stack alignment, and I give an example here. So say for this function, rt_printf. So this is a variable argument function, and so in the standard protocol, so the argument is aligned to 32-bit, and then the formatter can just take each of these arguments by an offset of 32-bit on the stack. But for C28, it's not such aligned, and so that means the argument handler do not know where to find these arguments in an accurate way. And to solve this problem, you can use a forced conversion to 32-bit for all 16-bit integers. So say so we have a forced conversion for the 1, 2, 3 here, and then it will be forcibly aligned to 32-bit. This is easy. And this one is a little more difficult, and that is because the memory and the stack is not aligned, and so it's not aligned in the same way as other standard devices. It's either 16-bit or 32-bit, and the 32-bit variables can only be put to the even addresses. So when you switch from 16-bit to 32-bit, you have to leave a gap here. And this is actually maintained by the compiler, which we do not have to worry about that. But the problem is when there's an interrupt occurs, and the interrupt is random, so the compiler do not know whether this interrupt occurs at some gap of the stack. And to solve this problem, TI just introduced two instructions, the SPA and NSPA, for realignment of the stack in the ISR. So in every ISR, you have to call the SPA first, and before you leave the ISR, you call the NSPA to restore the original stack pointer. And the problem is, because the context switch is also implemented by the interrupt, and so you have to do this SPA and NSPA thing for the context switch handling interrupt as well. But the problem is, so the SPA, so when you do the SPA, so that it will set a bit on the ST1 register, and this register is actually also stored in the stack as part of the context. And when you do the SPA in the context switch, ISR. So it changes this ST1 register, and then you trigger the contact switch, and you switch to the other thread. And then if you switch to the other thread, you restore the contacts of the other thread, which means so the ST1 register is taken from the step of the other thread, which is different to the previous ST1 registers. And you do the NSPA, so the NSPA have to use this register to decide if how it needs to restore the step pointer. But this NSPA is based on this register, which is not the same one as the previous context. And that means there's a mismatch in the SPA and the NSPA in the context handling, in the context switch handling ISRs. So this is really problematic. And to solve this problem, we used a workaround, and that is to only use 32-bit push pop in the ISR to handle the context switch. And because these 32-bit push and pop is not sensitive to the SPA bit, and then you do not have to use the SPA and the NSPA instructions in the ISR. And this solves this problem. And there's another problem which is quite similar to the previous one, is that the IER register, so the interrupt enabling register, is also part of the context, as I explained. When you switch to a different thread, so the ISR is taken from a different thread, which means if you enable the interrupt in one thread, it's not automatically carried over to the second thread. Problematic. And we use a technique called the context carrying over. So basically, so when we do the context switch, we know which is the address for the IER register of the step to be switched to, and we copy the current IER content to that address, which is carried over the IER register to the new thread, and so that the interrupt status is kept effective globally. And also, there's a problem for context switching within an interrupt. So we know that the context switch, so the thread cannot preempt interrupt, but interrupt can preempt thread. And this is quite a standard principle in operating systems. And for the mainstream device, say ARM, so this is very simple because the exception is to handle the context switch as the lowest priority. That means even you trigger this so the exception, it will not be handled until all the interrupt has been served. And this means so the thread will never preempt the interrupt. But for the C28 architecture, so the RTOS interrupt exception cannot be masked, and it also has no priority. And that means whenever you trigger that, it cannot be stopped. And this is very problematic. And to address this problem, we overload the RT interrupt leave function, which is called by each of the interrupt handler in the RT thread framework. And we insert these this function, these sentences into that function. And basically what we do is to see if there's any nasty interrupt being handled. And until all the interrupt has been served, we trigger this context switch. And this ensures that the context switch will not preempt interrupt. Yeah, and after we have done that, so we make a summary of what we do and the other say RTOS solutions, we make a comparison with TIs, native RTOS, and also free RTOS. We see that say the TI RTOS, it does not support contact switch within an interrupt. So that means we can't really preempt the thread. You have to wait for the thread to hand over the control back to the OS itself. So there's no preemption. And it's also the TI RTOS is not open source. And the free RTOS is pretty good. It supports both preemption and open source, but it does not support the latency. And the OpenPowerware based on RT-Thread is the only existing RTOS we know that supports both of the three functions. And the codes for these three OS cannot be found from the internet. Okay, so this is the finish of my presentation, and now I'm going to do a small demo of see how the RTOS is used for RTT used for motor control. I think you can all see my screen here, the camera. So the red one is the red one here is the MCU, and these are two motors to be controlled by the MCU. So one of the motor is controlled by the MCU, and the other motor is controlled by a motor controller. And so they can say, load each other. And then I just open the, I've built that and I've loaded that into the and I just click start. And after I click start, I open the shell. You see this is started, and we can put some command here. We can get the speed of the motor is not running. So the speed is 0, which is correct. Then we can set the torque. So you set the torque to 0.2. You can see, light symbol. And maybe you can hear the voice, and you can see the motor is starting to spin. And if I get speed now, it's running. And we can change the torque, and reduce the torque, and get the speed. And the speed is lower because the torque is lower. And then I started the other motor controller, and this is controlled by Simulink actually. So we can program the motor controller by Simulink. And we started. And because this motor controller runs the speed control, and we set speed reference to 0 and stopped. So the motor just stopped. And we get the speed here to see if it stops. It stops. Now we can change the speed. We slide this bar here. We change speed. And we can also see some waveforms. So this is the, for the motor control, so the amplitude of the current is proportional to the torque. And so the frequency of the current is proportional to the speed. If you reduce the speed, reduce the speed, we can see the frequency is actually reducing. To increase the speed, the frequency increases. And we can change the torque. Set the torque to say 0.5. We see that the amplitude of the current changes. To 1, which is 100%. We see that the amplitude further increases. And we can reduce the torque. Yeah, you reduce it. So the RTT gives us a very convenient way to do tuning. You can also change parameters via the shell. You can set command and read debugs. So this is very convenient, and I love it. Yeah, so this is the end of my demo, and I hope you like it. And thank you for your attention.